Hi, in this video, I'll be going through the irreducibility criteria for polynomials. So, in the previous video, we have already seen by Gauss' lemma that it suffices to consider the factorization in fx where f is the field of fractions of R when R is your unique factorization domain. And so, we shall consider the case where there's only one variable now and list some ways for us to find a mechanism to determining whether some polynomials are irreducible or not, meaning whether they can be factored out or not. And so the first proposition we have is if we have a polynomial in this fx, then px has a factor of degree 1 if and only if px has a root in f. Meaning there exists an alpha, an element of f, such that p alpha equals to 0. And so the proof follows if it has a factor of degree 1, and since f is a field, we can just assume the factor is mononic because p alpha equals to 0. You can just pull out the x minus alpha, and even if the p is not, or if it's like 2x minus alpha, then because it's a field, you can just divide out by 2 because it equals to 0, so you just divide by 2 and it's cancelled out. So we just consider the monic factors, and it's the form of x minus a. But then we know p alpha equals to 0. So alpha is a root. So now we consider conversely, suppose p alpha equals to 0. By the division algorithm, we can write it as the following. And then we just sub it as alpha. So this is 0 and then this is 0. So r must equals to 0. And so px must have a factor of x minus alpha as a factor. So this is a very easy proposition, but it will help us in a long way. So now, a polynomial with degree 2 or 3, so it's like 2 or 3 small degrees, is reducible if and only if it has a root. And this follows immediately from the previous, because since a polynomial of 2 or 3 is irreducible if and only if it has at least one linear factor, the next result limits the possibilities of the root with integer coefficient. So if you want to understand why it's so, because if it's degree 2 then it's x squared, then if it's reducible then you can pull out like a linear factor, so then it must have a root by this proposition. And if it's a polynomial of degree 3, then it's like x cubed minus 1, let's say, then you can still pull out a linear factor, and the other one must be a quadratic, so it must have a root. But if you have like maybe degree 4, then it's possible that for degree 4 it's like x4 minus 1, then it's like x squared minus 1, x squared plus 1. But in maybe a case where the x squared plus minus 1 is not able to break down, then it's reducible only to polynomials of degree 2 each, so you can't tell if there's a root. So because degree 2 and 3 are small and they must have at least a linear factor, then there must be at least a root. So now we'll look into the case where we have integer coefficients. And so we let px be a polynomial of degree n with integer coefficient. If r divided by s is an element of q, is in its lowest term, means they are relatively prime, then r divided by s is a root of px, and this is a root of px. Then r divides the constant term and s divides the leading coefficient of px. I to say R divides A naught and S divides AN. In particular, if Px is a monodic polynomial, if S divides AN, then it must be S divide 1. So S must equals to 1. And so PD is equal to non-zero for all integers d dividing the constant term Px. Then Px has no roots. So we must take a look at what's happening. So by hypothesis, P of Rx equals to 0, meaning you can just sub in Rx into the polynomial. And then you multiply throughout by S to the power n, and you get this new result. And this whole thing must still equals to 0, and so then you pull out A to the power Rn, you bring this whole thing to the other side. Then you pull out the S, and you get this following result. So S must divide AN times R to the power n, but since S and R don't have any common factors, that means S must divide AN. And with that, you can similarly solve the equations for A naught Sn. Because now you keep this, you bring this whole thing over, pull out the R, and you get that R divides A naught. So some examples will be the polynomial of x cubed minus 3x minus 1 is irreducible in the integers. And you can just show this by showing that there is no rational roots. And by proposition 11, then the only candidates for rational roots are integers that divide the constant term 1. And so when you substitute both 1 and minus 1 into the polynomials, this shows that these are not roots, and so we're done. So you can see example 2 again, where you have the polynomials x squared minus p and x cubed minus p, where p is prime, are irreducible in the quadratic polynomial ring, the rational polynomial ring I mean. And this is because the degree is less than 3, so you can just suffice to show that they have no rational roots. By proposition 11, then the only candidates for the roots will be just plus minus 1 and plus minus p. But none of this gives you 0 when they're substituted into the polynomial, and you're done. And lastly, the polynomial x squared plus 1 is reducible in this quotient ring since it has 1 as a root and its factors as x plus 1 squared. So you can just check, because when you sub 1 in, it's just 2, and 2 factors out to be 0 equals, and 2 is 0 in this ring, so you can just factor it out. Next, you can check that this polynomial is irreducible in this quotient ring since it doesn't have a root when you sub in 0 or 1. Similarly, the polynomial x cubed plus x plus 1 is irreducible in z over 2z. So you can take a look at more examples in the textbook to better understand how to use this proposition to determine whether a polynomial is reducible or not. Next, we look at this where we say that we let I be a proper ideal and Px be a non-constant monodic polynomial in Rx. If the image of Px in the quotient ring where R is divided by I cannot be factored into two polynomials of smaller degree, then Px will be irreducible in the original ring, polynomial ring. So we just need to prove it. So we suppose that Px cannot be factored in the quotient ring but we suppose that Px is still irreducible in the original ring. As noted at the previous video, we can just let Px equals to Ax times Bx because it's reducible, and then by reducing the coefficients by modulo I, because you can create a ring homomorphism, this gives us a factorization with non-constant factors, and so this is a contradiction. So this shows that if you are able to find an ideal that a reduced polynomial cannot be factored, then the polynomial itself is irreducible. Unfortunately, this doesn't help you tell whether a polynomial can be reducible, because even if you check a lot of ideals, you need to check all the ideals to see whether it's irreducible or not. So there are examples of where polynomials are irreducible, but in every ideal they are reducible. For example, the polynomial x4 plus 1 is irreducible in Z, but reducible in every prime. And we will check this next time. And so some examples of using this proposition is we consider the polynomial x squared plus x plus 1 in the integer coefficient polynomial ring, and we modulo 2 it. And we see from the above example that Px will be irreducible. And similarly, x cubed plus x plus 1 is irreducible in Z because it's irreducible in Z modulo 2. Then the polynomial x squared plus 1 is irreducible in Z since it's irreducible in Z modulo 3. But even though you can see that it's reducible in modulo 2. So this shows that the converse does not hold. So what we really want to do is we need to find a correct ideal for this to work. And this could take a while because you need to do trial and error. Next, we see a special case of reducing modulo an ideal to test for irreducibility, and this is known as the Eisenstein criterion. So the Eisenstein criterion states that if P is a prime ideal of an integral domain, and we let fx be a polynomial in this Rx, and suppose that an to a0 are all elements of this prime ideal, and then you suppose that a0 is not an element of P squared, then fx will be irreducible in Rx. So what you need to check is that you need to check that all these coefficients are elements of the prime ideal, and that a0 is not an element of P squared. Then you already know that the polynomial will be irreducible. So we suppose that fx is reducible, then it can be broken down into factors. Then we reduce the equation using modulo P. And by the assumptions of the coefficients, all these will be cancelled out very fast because they are elements of P. So you left with xn equals to some factor in this quotient ring, and because P is a prime ideal, R divided by P will be an integral domain as well. And this follows that both AX and BX have zero constant term. i.e. the constant term of both ax and bx are elements of P. And so, the constant term a0 is a product of these two elements of P squared, which is a contradiction now, because a0 is not an element of P squared. So we can see that this criteria is very frequently used, and a corollary of that is when you already take it into integer coefficients, then it's reduced to saying that P divides ai for I 0 to n minus 1, but P squared does not divide a0. So we'll take a look at many examples now to familiarize ourselves how to solve questions in this, and one use of the Eisenstein criterion can be applied to this polynomial, where we choose the prime 5, and because these coefficients are at 5 divides these coefficients, but 25 don't divide 5, we show that this polynomial is irreducible. So let's take a look at some examples to help us, and we'll show that this polynomial is irreducible in the integer coefficient polynomial ring. We just need to use Eisenstein criterion for p equals to 2. Then we see these coefficients are all divided by 2, but 4 don't divide 2, and we're done. And now we see the next example and show that x4 plus 1 is irreducible in zx. So we suppose that it's reducible, and we can break them up into these factors, and then by expanding the right hand side, we just need to multiply them out and solve the equations to get a contradiction at the end. So this is really routine, and I'll leave it to you to read it, but it's really working through the algebra where you break it down into this reducible, and then you just multiply throughout and expand out the coefficients one by one. So you get a contradiction in all cases, and we just shown that it must be irreducible in this case. So you can see how there are many questions about checking whether a polynomial is irreducible, and I'll leave it to you to try out in the textbook. I've introduced some methods for you, such as the Eisenstein criterion, Gauss lemma, and many others that are not named. That's all for this video. I hope you have enjoyed it. Please feel free to like, share, and subscribe, and I'll catch you in the next one. If you have any other comments, you can leave it down in the comment sections below. Bye!